So today's topic is network arch bridges. Firstly, let's look a bit into what network arch bridges are. The concept of network arch bridges implies the fact that the hangers for the arch that connect the arch to the tie should be inclined, and these should pass each other at least twice. With this type of structure is very similar to a truss structure, and the top part of the bridge, namely the arch, will work in compression, and the bottom part, the deck or the tie, will work in tension. Most of the shear for this type of structure will be taken by the hangers, and there is little shear in the arch and the tie. Also, because of the way the forces are distributed with this type of hanger arrangement, there is little bending in the arch and in the tie. This type of bridge was firstly developed by a Norwegian engineer, Per Tveit, in 1950s, and the first such bridge was constructed in Norway in between 1963 and 1964. And you have the schematics of the bridge on the right. During the same year, other two bridges were constructed with this technique, another one in Norway and a different one in Germany. Now let's see some advantages of this type of structures. One of the aesthetical advantages is the fact that these are very slender structures, and so that they don't cover the landscape, they blend in very well, and they have a very pleasing look. Also, from a structural point of view, these are very stiff, so they are very suitable for railway bridges. And if these bridges are designed properly, they can lead up to 50% of savings when it comes to material. Also, from the research done until now, and the bridges constructed until now, these are very suitable for spans between 60 and 300 meters. Also, because of the cable arrangement, because of the hanger arrangement, these are not sensitive to uneven loading or uneven settlements, which is a big advantage. And also because they have a high resistance, but because of the weight that is very low, these are very good in earthquake zones. And from an economical point of view for the community where these are constructed, because these use a lot of, not a very large quantity of materials, a large part of the cost of constructing such a bridge goes into wages. So this helps the local community and decreases unemployment, and also decreases the impact on the environment. Now let's see how this type of bridge compares to other types, arch bridges with vertical hangers. As you know, arches are very efficient structures, and work very well when the load is evenly distributed along the arch. But the problem comes when we have uneven loading. So I just took a study case here with two bridges with the same dimensions of the arch and almost the same number of hangers. The one with the vertical hangers has actually more hangers than the one than the network arch, and loading it with uneven loading. So let's say this would be a live load on half of the bridge. When we compare the results, the displacements, we can see that the deformed shape of the one with the vertical hangers is much more pronounced, the deflection, whereas the network arch has a much better behavior when it comes to uneven loading and displacements. As I've mentioned before, it is much stiffer. Now when it comes to bending moments in the arch and in the tie, for uneven loading we can see the distribution in the vertical hangers. It is very unsymmetric. So half of the arch will work with negative bending moments and the other half with positive bending moments, and everything, the distribution is very different on the two halves. Whereas when we take into account, when we consider network arches, we can see that the distribution of the bending moments is much even and a much better distribution. Also, I've taken a case study where we assume that we have some damage to the tie. So I've considered that by releasing bending moments. So considering that we can't carry bending moments anymore in the tie, so here is where the damage is considered, and in the vertical hangers model, we can see that after applying the damage, the redistribution is as the one below. We can see that this increases very much the bending moments close in the arch, close to the position of the damage. Whereas if we do the same for a network arch bridge, we can see that the bending moments are much better redistributed in the rest of the structure, and we don't have these peaks, just as the ones in the one with the vertical hangers. So even when we have damage in the tie, we can see that network arches behave in a much better manner. Also, another comparison, very important comparison, is the comparison between materials. We have here a graph. We can see that the first bridge is a bridge built in Norway. It's a network arch bridge with 135 meters span, and we can see the materials, the kilograms per square meter of steel needed, and the top part is steel, structural steel, and the bottom part is reinforcement. And we can see just how much steel this type of bridge can save when it is designed properly. To compare it to a bridge that has almost the same span, which is the Jerusalem Bridge, we can see that we can get even 4 times less structural steel needed for a similar span. The network arch bridge is 135 meters, whereas the Jerusalem is 130, and we can get a better savings in steel, even compared to bridges that have smaller spans, such as the last ones. Now let's look a bit into the components of this type of bridge. Firstly, the arch. The arch can be built by either using concrete or steel, but the preferred material is steel. Also, the preferred shape would be a circular shape, but the parabolic one can be used as well. And when we use a circular shape, there have been some research conducted on this, and it has been concluded that if we decrease the radius of the circle towards the ends of the bridge, we can get a much smoother distribution of the bending moments. And the arch is, as mentioned before, is mainly loaded in compression, so the axial force dominates in this type of bridge. If we again compare the effects in the tie with a similar bridge, so the bridge with the vertical hangers is a bridge that is constructed, and then the top one, the network arch, is a proposal by using almost the same steel consumption. The results have been compared between the two, and we can see that in the influence lines for the bending moments in the arch, the network arch, the curves here, are much smaller than the ones compared to the one with the vertical hangers. For the arch itself, it is recommended to use a universal column or an American wide flange column, and usually the best solution would be for it to be placed with the weaker axis in in the out of plane of the arch, which helps with the connection of the hangers to the arch itself. Obviously, for other bridges, tubular or circular sections can be used, but these increase the cost significantly. And because if we are to compare the same area of steel for a universal column to a tube section or a circular section, we can see that the sizes of the tubular section are much greater, but because the arch is mainly loaded in compression, there is no need for a large moment of inertia. So again, structurally and aesthetically, this would be a better option. Also, using a universal column decreases, as I said before, the dimensions. The details are much simpler for this type of section, and also we need less weldings. It is also much easier to install everything on this type of section. And when it comes to the connections along the arch, the connections that are needed for the arch can be done very easily with bolts, and the bolts in the flanges, for example, are structurally needed mostly just during the assembling, because there are not large bending moments in the arch, but these are usually kept within the structure, in the completed structure as well. We can see in the lower part a connection between the tie and the arch itself. When we use a new universal column, this is very easy to do. And also we can see in the bottom right corner how a connection with the wind brace will look. Now the next component, the hangers. Hangers can be done using wires or rods, and these are always high steel strength. Generally they have a small diameter between, say, 40 and 60 millimeters, and as these are the hangers, when they are loaded, they take only tension, and when they don't take compression, so they relax instead. And this is one of the things that needs to be considered when carrying an analysis for this type of bridge. Also, the placement, the distribution of the hangers is very important. For example, if we want to not have much relaxation in the hangers, we need to look at the steepness of them. So steeper hangers mean generally more relaxation. The placement of the hangers along the arch should be as equidistantly as possible in order to load the arch more evenly. And as these cross each other, when after installation, some plastic tubes are placed so that this makes sure that the cables don't bang against each other, and also the plastic tubes need to allow for some relative rotation between the cables. Also, when analyzing this type of structure, when we do the final state analysis, we need to find the optimal hanger arrangement. There are several methods which can be used for this, or we can use trial and error if we have something in mind. And usually some research has found that the radial arrangement, such as the one presented here, is one of the most efficient. Now the last component, the tie. The tie again can be done just as the arch, using concrete or steel, but for many bridges, and especially for those that are not very wide, concrete decks are preferred. Again, the arch works in tension, so when using the concrete decks, pre-tension is used. Pre-stress is used longitudinally, and for ties where the lower beam and the deck are built together, transverse transverse pre-stress is generally used as well, because with this type of bridges, The transverse bending can be larger than the longitudinal ones in the tie. And another advantage of using concrete decks would be that because of the weight of the concrete, these help with tensioning the hangers, so we have less relaxation. Also, as mentioned before, these are pre-stressed, so the pre-stress will very likely improve the durability of the concrete. During the erection process, again, either when using concrete or steel ties, it is very usual to use temporary steel ties, just as the one here. We can see the temporary one, which is used during erection and then taken out afterwards. On the right, we have the comparison of the same bridge, just as here, but this time the comparison of the influence lines for the tie. So we can see the bending moments in the lower chord are much lower when we consider a network to arch compared to one with a vertical hanger. So again, another plus for the efficiency of this type of structure. Now let's look at the erection process. There are basically two types of construction methods that can be used, two big categories, let's call them. We can build the network arch on site. So just as the one here, we can build scaffolding or temporary supports, and we can build the arch. Or we can build the arch off-site and then place it in. For this, we have mainly two categories of ways of doing it. One is building it off-site and just placing it on the support, as we can see here. This is very efficient when it comes to bridges that pass over water. Or the second option would be, again, building it off-site, but using incremental launching. So we can build the arch either off-site, bring it to the site, and then incremental launching, or we can build it next to the site and then just launch it again. We can see an example of the process here. Now let's look into the analysis types needed for this type of bridge. For this, we have mainly three analysis types. We have the static analysis, construction stage analysis, and a time history. The static analysis is used in order to get the hanger. Firstly, we get the hanger arrangement on the static analysis, and this type of analysis uses the correct geometry of the bridge, because we consider that in this type of analysis all the cables are tensioned. We don't need to use cable elements as in cable finite elements, because everything is tensioned, so truss elements should be enough. In Midas Civil, we have two functions that are very helpful for this, namely the unload load factor used for the initial pre-stressing in the cables, and cable force tuning, which is used to tune the pre-stress in the cables. I will explain the unload load factor first. As mentioned, this is used to find the pretension in the cables so that we satisfy given conditions. We call them constraints, and we can define certain constraints such as reaction values, displacements, or forces, and we set up the constraints and then choose the pretension values, choose a load combination which has the pretension values, and the software will find the optimal solution, the optimal values in the pretension, so that the constraints that we put in are satisfied. This option cannot be used with cable elements, because the iteration needed to recalculate the stiffness using cable elements cannot be done within the function, so truss elements are needed. But as mentioned before, for the static analysis, there is no need for this analysis. There is no need for cable elements, so trusses are enough. Let me show you in a model how this is used. I have here a model with the final stage, so the entire geometry modeled. I don't have any construction stages in this model. I have different sections, again, as you can see for the model, the support conditions, and 2 load cases. I'm considering the self-weight applied using the self-weight function, and superimposed dead load, which is just applied as UDLs along the deck. And I also have pre-tension forces in all the cables. Let me just display some of them here. So I have one pre-tension load case for each couple of cables. So in total I have 30, as I have 60 cables, so I have 30 cables in this model. Also, in order to use the unknown load factor, we need a load combination. So I've basically run the analysis on this, then created a load combination which has the self-weight and the superimposed dead load. Again, this is for example purposes, but for the bridge we can use the factors that we need, the safety factors that we need for the loadings on the final structure. So I have the self-weight and the superimposed dead load, and then all the pretensions are with a scale factor of 1. Also, the pretension applied on the cables, as you can see, has a value of 1. After running the analysis with the self-weight and the pretension, we can go into results, cable control, and unknown load factor. Here we can create a function, an unknown load factor function, and then we have several options here available. Object function type. This is related to how the results should be checked. So the software, we have 3 types: linear, square, or absolute max. The object is the equilibrium condition that satisfies the constraints, and as we have different types of solutions for the constraints that we applied and tension forces, the software checks these solutions between them and takes the most suitable one. And then the sign of the unknown, we can choose to have the scale factors either be only negative, positive, or can be either sign. And the simultaneous equation method can be used when we have the same number of constraints as number of unknown loads. So if we have the same pretension forces as the same number of pretension forces as number of constraints, then we can use this function. Here are the functions that I just explained. Here is the combination that I've created, and then the constraints, as you can see, we can add a name and choose what type of constraint we want to have: a reaction, a displacement, or a force, either in a truss or in a beam. Then we can assign the node that we want to constrain, or the element if we choose forces, and also what component we want. And then we can give conditions to these constraints. So in this case, I don't want my deck to go between more than 2 centimeters upwards or downwards. And after defining, what I've did was just simply define the constraint along the middle of the bridge, so these nodes here. After defining the constraints, we can get the unknown load factor. Here we choose that the self-weight and the superimposed dead load should stay as they are, and the ones that are scaled with the factors should be only the pretension loads. And having the unknown load factor, we can see now that the self-weight will keep a factor of 1, superimposed dead load would keep a factor of 1, and the pretension forces have factors assigned to them. And we can see the value of the constraint, if it's within the limits or not. We can see this with the influence matrix as well, if you want. And what we just need to do now is just make a load combination, give it a name, and then this will automatically create a load combination that has the hanger forces, the scale factors defined there, already added in the cable forces, in the factors for the pretensioning. So now we have the initial pretension in the cables directly. These are the values that we need for the model, and these can be used afterwards in the construction stage analysis. Another useful function that can be used is cable force tuning. This is used to optimize the tension in the cables. It is very useful as in the results that we see are in real time. So if, say, we have found the initial pretension force in the cables for the dead load and the superimposed dead load, and then we run the moving load analysis and we find the critical vehicle position for a given element, we can take this, put it in a load combination, and then with a cable tuning, force tuning option, we can simply change the values of the pretensions so that we can see the effects directly in the model. Here I have chosen a load combination. This time I'm taking the one with the hanger forces. And then we can choose to have the results shown here. We can define what type of results we're interested in. We can define a group. Just to show you, I have a group here called tie. So I'm interested in the effects along this side of the bridge, so the tie in this side of the bridge. And we can define displacements, as in this case, or beam forces. Again, we can check stresses as well, or truss forces. So we can choose one result. If we want, we can show two results at the same time. So I'm checking displacement in the deck and bending moment in the tie along the length of the bridge. And here, if we want, we can put in some limits. So let's say lower limit should be 0.005 and say 0.01. Let's make this 1 and 1. And we can see the range here. And for the bending moments, let's say we have minus 200 and 150. And then we can see the range, and then simply by either modifying the value here in the cable or by simply dragging this, we can see the effect in the cables directly. We can see the effect for the results directly. So we can increase, decrease, and we can see in real time the changes that happen in the structure. Obviously here we can define many functions that we can check these as well. And if we want, we can either save this as a load combination, or we can update the model with the values that we have chosen to be the correct ones after the tuning. So this is how we can get the initial this is how we can get the pretension force in the cables using the static analysis. Then we can use these values to go in the construction stage analysis. Now the second type of analysis, as mentioned, is the construction stage analysis. With this, we can consider if we want the nonlinear behavior of the cables, and the construction stage analysis shows the construction sequence, so the actual construction of the bridge with all the temporary supports depending on the construction sequence that we choose. Now, as I've mentioned before, this can use we can use nonlinearity of the cables in the construction stage analysis, but it is not that easy to decide if we need nonlinearity or not. So as mentioned before, with the final stage analysis, with the completed model, we can get the initial cables in the forces. And if the forces that we get after the tuning are above 70% of the ear force in the cables, then these, as mentioned before, will behave such as exactly as truss elements, because the bridge is very stiff. So it is generally not a need to do a large deformation analysis for this. As a rule of thumb, very large span bridges above 600 meters generally require nonlinear analysis. So in this type of bridge, it is basically up to the design engineer. As mentioned before, there is no way of not a specific criteria that asks for this. So a very common approach is to run both a linear analysis and a nonlinear analysis, and then compare the results, see if the nonlinear analysis is needed. Now let me show you the cable, the construction stage model. Here again, I have the same model. This time, I've generated the construction sequence. In this model, I'm using tension only, so I'm using cable elements this time. Let me show you the construction sequence. So I have firstly I'm constructing the deck. Let me show you the supports as well. With temporary support. So we start with the deck with temporary support. Then construct first part of the bridge with temporary supports again to hold the bridge. And then we can start installing hangers. Hanger number 1, 2, 3, 4. We keep again, this is very dependent on the case. This is one construction sequence. Others can be where the cables are installed from both sides at the same time. And after finishing the installation of the cables, we can start removing the temporary supports. And in the last construction stage, we have the geometry exactly as in the final stage model. So the complete the bridge as it is constructed. Now again, I'm using the same load cases, but this time the pretension forces used are those that we have found from the with the unknown load factor. So we get the factors. We can simply copy these in the pretension forces and apply it to the model, to the pretension forces. In the previous model, these were values of 1, but this time we have changed them to the cable tension forces from the found with the unknown load factor. When running the construction stage analysis, we need to use the cable pretension force control, and in this case the external forces. So then we can find the correct values and check if the correct values in the cable forces at the end of the construction stage are the ones that we need for the final stage. As mentioned before, during the construction stage analysis, we can include nonlinearity as well. And for this type of bridge, we would need the cumulative stage because we're using a forwards analysis, so constructing the bridge from 0 to the end. And after running the analysis, we can read the cable forces. We can read them between stages, but the ones that are important at the end, we need to make sure that the ones that we have at the end are those that we have found using the final stage analysis. So we can check the pretension in the cables, and we can also do it in table format for the last construction stage. We can check the values. We can take this into an Excel and check it against the values found from the final stage model, and they should match. If they don't match, then it means that we need to tune these. And again, just as before, this time we can use the unknown load factor, but the unknown load factor also works with construction stages. So what we can do, if we don't have the same values of the stresses in the cables at the end of the construction stage, we can carry down a load factor for the construction stages as well. So we can choose a construction stage and add the constraints again. This time we can check the displacements if they match or not, and we can use as constraints displacements, and also we can use the forces in the cables themselves. And then again retune, carry the construction stage analysis again, and then go and check the forces, the tension forces in the cables at the last construction stage, see if these match. So in this way we can find the correct jacking force for the cables and match it to see if the correct values at the end of the stage, of the construction stage, are those that we need. After the construction stage analysis, another case that might be worth looking into is a time history analysis, and mainly we can look into the snap of a hanger. So we can consider also in Midas Civil, we can check what happens to the structure if one of the cable fails, say a car hits a cable, or it has a fault, and we can check what happens with the structure afterwards, so we can see the behavior. And this can be very easily done using a time history analysis and using dynamic loads. Let me show you how this can be done as well. I have here a time history model. I'm using the exact same model as the one for the final stage. Again, I have a load combination with the factors from the unknown load factor. So these should be the final forces in the cable, and the self-weight and the superimposed dead load. And what I have done was remove one of the cables. Again, I'm using truss elements for this. So what I'm considering that this cable over here snapped. So this cable here snapped. And what we can do, we can run a time history analysis applying a dynamic load opposite to the tension forces in the cables. So I took the tension force in that cable from the final stage model, and also using node query, element query function, I have taken information about that cable, what angle it has with each plane. So knowing the force and the angles with the plane, I could decompose it very easily in an Excel. So I have the information here about the element, the force that was in that cable, and the angles with the planes, and then I could get the decomposition of the load along the three directions. And I've created a static load case with these loads. So I'm considering the force acting in the opposite direction of the tension force in the cable. As you can see here, I've decomposed it over the three directions. This is a static force, but what we can do is apply this static force as a dynamic load. So the time history load case that we're interested in this case, would be a transient load case. I'm assigning an end time, a time increment, and how many number of increments I want for the outputs. And again, we can use linear or non-linear time history analysis. As mentioned before, this is 90 meters in span, so I'm considering, and these are all tensed. The tension force in the cables is as for the final model, for the final state. So I can use linear analysis for this. And as mentioned before, I have the load case with all the pretensions I have a load case with all the pretensions in the cables and the self-weight, and I've created from a load combination of these, I've created a load case here, and so that when the hanger snaps, the state of the bridge before the snap is that as if being loaded with the self-weight and the pretension in the other cables, and obviously we can assign the damping as well. So these are the settings for the time history load case. Obviously this is a transient load case. As mentioned before, we can use linear or non-linear. In this case I'm using a linear time history analysis. And the load, as mentioned before, it is defined as a static load, but to apply it we will simply convert a static load into a dynamic load. I'm creating a function type normal, so this means that this is a scale factor that is applied on the dynamic load that I'm using. I'm choosing to have first step 0, at 0.1 of a second I have 1, a value of 1, a scale factor of 1, and then 0, so I'm basically, it's an impact load as the hanger snaps. Using this function I can apply the dynamic load simply using a time varying static load case. So I use the function, I'm using the static load case hanger snap, the one that I have just shown. So this one here, and I'm telling it when to arrive and what scale factor. So it arrives at 1 second during with a scale factor of 1. After running this analysis, we can check the behavior of the bridge. Let me show you here a video after the snap. So these are the deflections after the snap of the cable. Okay, the video doesn't work, so I will just show it directly on the model. So I have run the analysis, and now to check the results, we can check time history results. The time history load case hanger snap, the one that I have defined. And we can check both displacements, velocities, and accelerations. We can check the displacement at each step, or if you want, we can animate this. So say we start from 0.9. And now I can see the behavior of the bridge. Just a second for it to load. And now we can see, so the snap happened, and now we can see the deflections in the bridge. We can see how the bridge dissipates the energy and how the cables behave. Obviously this is good for visuals, but what we're interested in are numbers. So we can very easily read graphs or table results for this. So for example, let's say I'm interested in the displacement at the node right in the tie, right where the snap occurred. So we can create a graph using a function. We can use any result that we want to show in this graph, and we can give it a name, choose what we're interested in, what component we want, and reference point. So I'm checking the DZ deflection for the node where the cable snapped, and I can check the behavior of the deck at that point along the time history, a long time. So we can see no load, then the snap occurs. I have the maximum deflection, and we can see just how rapidly the deflections come to zero. As you've seen in the time history load case, this is 20 seconds. Similarly, we can check the results for the accelerations in the bridge when this happens, just as the displacements and the velocities. We can check with the codes if these, if in this case the bridge behaves as it should. And this is everything for this webinar. If you have any questions, please write them in the questions box, and I will try to answer as many as possible.